out. Sometimes it's smaller, sometimes it's bigger, and you have to redesign. So at least one iteration you have to do. Type of wind tunnel is it'll be determined by two factors, I believe. One is technical and one is financial. Everybody would like to get the best husband and wife. They want it rich, healthy, nice, whatever. So everybody wants to have the biggest tunnel he can have, highest speed as possible, but then everything costs. Space, first of all. Sometimes space is very small. Not every place is so large. And faculty is not giving you so much space. And then budget. Usually budget is the story, and you are limited to start with some amount. What happens? You calculate, and you come up with total cost, but take in account that it'll jump up. It will increase, because if you are not a customer, if somebody else is your customer, somebody else is your sponsor, you come to him and tell him, hey, I can buy this, I can buy that. I can buy variable fan blades or constant blades. What do you prefer? So if this is somebody who is interested in the project, he say, why should I save? So let's get the best. So you sum up it finally with much higher price, much higher cost. You have to be careful with that. If you appreciate that you'll get the budget, go ahead. Take the best all the time. That's what I was doing in Tel Aviv. Students' estimate for the cost was 200 shekels to start with. Only the structure, not measuring elements, structures. And system by system, we bought the best. And we came up with half a million shekels, which is multiplied by 15. You get it in rupees. How much is it? Huh?
75 lakhs.
Okay, 75 lakhs. And it's cheap. If you have to buy that one, such a wind tunnel, I'm sure you'll buy several times more. Yeah. Once we decide what type of wind tunnel we have, we go element by element and we calculate first the features of every section, and then we calculate the loss, the energy loss, pressure loss. Thanks. And out of that, we come up with the power requirement. Once we know what is our energy loss in the circuit, we can choose our power plant, our power. And practically, wherever you look, you don't find finally the same speed that you were calculating. Always there are surprises. And surprises always is to decrease, to put you down. So take in account, take some extra power. Anyway, it's better to run not in the full power and something lower, because the full power will always be noisy. So you better buy something a bit stronger. The motor will be something stronger, and then you lose and you work only 80%, 70% for the maximum need. And then you get the flow velocity. And what I've mentioned before, it's you get the typical sections, the functionalities, and then the loss you calculate, and you get, and you start detailed design of your wind tunnel. So it's very simple, very easy to remember. You start with the overall look, overall requirement, environment, and then you start designing your test section and go ahead from there. If you are for low speed wind tunnel, you should be below 0.3 max. Otherwise you start compress the air, power will increase dramatically, no need. Because for 100 meters per second, which is roughly 0.3 Mach number, you get 7 million Reynolds number per meter. This means if you want to have transition, after 10 centimeters you get the number. You get higher than 500,000 Reynolds number. So after 10 centimeters, your boundary layer will change to turbulent boundary layer, which is something that you don't like too much, because then you need to compensate for the walls. Once your boundary layer grows, it means the practical test section size decreases, and then velocity increases. You have a pressure gradient. This is something you don't like to have. You would prefer the boundary layer to go slow, and so the static pressure along the test section will remain practically constant. If you have this pressure gradient, you get similar phenomena like hydrostatic force, like what you get with respect to gravity. In hydrostatic, you have change of pressure along with the height, with level, and then with altitude. But when you have this pressure gradient along your test section, you get the same phenomena. You get pressure gradient as a function of distance. Something not healthy, because then if you have a long model, you get a pressure gradient along the model which is not simulating the real flight. Let's say usually we are satisfied with 50 meters per second test section. It means even after 20 centimeters already, you got capabilities, you got a situation to get transition. But as I mentioned before, 500,000 is only necessary, but it's not sufficient. If the flow is really quiet, you may postpone your transition further down. And the same with the model. So if you want transition on your model, natural transition, you need a model of that size, so you'll get transition. But since your velocity is lower than real flight, you again have to trip your boundary layer to get transition on your model. There are some rules, empirical rules that were found after experimental experience. And one of the rule of thumbs that your Reynolds number based on momentum thickness should be something like 320. You mean you multiply your Reynolds per meter by the value of momentum thickness. Momentum thickness is again displacement thickness over 2.6 for laminar And from that you can calculate, by knowing what is your x, what you be, and what you will be your Reynolds number on your model.
This x is length of the section or
Yeah. No, length, it's the distance on the model.
distance?
On the model. One important issue is if you're working with two-dimensional profiles, they shouldn't block more than 25% from your cross-section area. Once you increase your angle of attack beyond 25% blockage, if the frontal view, the frontal area of your model is more than 25, it will affect your coefficient, your forces. Then the blockage will accelerate the flow, and you'll get deviation of your polars. This is something reported in many papers, and you may see it even by yourself.
So this 25% block is only in the case of low speed tunnels? Or?
Yeah.
Is there any technique to remove the hydrostatic grading? What you are telling, sir?
I have to repeat your question because yesterday I watched a video,
Yes.
and I saw that I'm answering and nobody heard the question. So once it is relevant, and usually your questions are relevant, I will repeat, asking if there is any way to overcome this pressure gradient along the test section when it happens. Usually it happens. But sometimes it's very low and you don't care too much. But once you feel and you measure your static pressure distribution along the test section and find out you have a reasonable one, I mean significant one, but you can find it from ahead. Then you have to diverge the walls
Yes, section.
on that. So you can beforehand calculate what will be your displacement thickness. You can estimate the worst case, that you will have a turbulent boundary layer from some place, and then diverge the walls according to that amount. They're small numbers, but you want to be on the safe side. Usually on the instructing wind tunnels and the preliminary design, we didn't take of this. It's complicated production because we ordered the test section. Usually ordered it's aluminum and plexiglass structure, and usually they are not planned to have this kind of diversions. They have only straight structures. It's visible, but investment is not always needed. So I mentioned some of the things. I'll repeat. Models will be tested mainly in this size of wind tunnels in square or rectangular shape, cross-section shape. And we say if it is a model with wings, it won't occupy more than 70%. The span will be not longer than 70% from the test section width. Otherwise, you'll get a disturbance on your flow, which will be significant. It changes the flow, and then as many calculations you make, you are working on some disturbed model, and that's not what you are looking for. So we prefer to be on the safe side, 60% at most, but if nothing happens, nothing can help it out, we work on up to 70%. As a rule of thumb, we are satisfied with two lengths. The lengths of the test section should be like twice the longest size of the test section. If it's rectangular, it's the side and so forth. Or if it's something complicated, it will be hydraulic radius or diameter, actually. We define hydraulic diameter here. For automobiles, ground transportation, we are satisfied with 5% blockage from the cross-section area. But usually, as much as they look rough, those wind tunnels, they have long test section to follow down what happens. It's very important. The main issue there is the drag. You saw it in the Mercedes video. It's very important to look down how the shape is affecting the drag. So for our purposes, usually, academics and preliminary design, test section size between 0.1 to 0.5 square meters would be quite satisfying. 0.5 mean 70 centimeters square, 0.1 mean 30 centimeters squared. We can do good work. But let's say industrial wind tunnels, usually they have bigger ones. They will have, as I mentioned yesterday, 3 meters like that, 3 meters side. Yes.
Is frontal area or instantaneous area of cross section?
Please repeat.
The blockage,
Yes.
whatever percentage you are mentioning.
Yes.
So whatever we need to consider is the frontal area, even with the model having
Yes.
angle of attack,
Yes.
or is it instantaneous cross section?
Start with cross-section, whatever it is. In automobiles, ground transportation, it makes no difference. But yes, when you increase your angle of attack, you better look at the frontal area. It will be meaningful then. It's not enough just to have the cross-section.
If this section is like it's having height more and width smaller.
Yeah.
If in that I'll put my wing in vertical position,
Yes.
and suppose second tunnel which is having width more,
Yes.
height less, I'll put it in horizontal position.
Yes.
So whether these results are different or
Well, you don't care as long as your distance from the walls is not too close. One factor is the blockage area, which it doesn't matter if you are rotated or not. But the other factor is the closeness to walls. So it doesn't matter. There are many wind tunnels. There are many rectangular shaped wind tunnels. And you can see people are mounting the models anyway. It could be even inverted. The flow doesn't find any difference if your model is inverted. Where are we? Oh, there are problems there. If you have the budget and space, you would prefer to work in a closed circuit, because then you don't have to take care about the environmental issues. People will not disturb you. Not anybody will open the door, then it will change your velocity in your test section, something like that. So you control your testing. If you are sure you can control the environment, you can go for the open loop because it's less cost, and also could be even more easier to control the turbulence level there, because in the closed circuit here you have these turning vanes and all the elements that adding noise to your flow. Then you have to work again on decreasing all the disturbances. Where in open loop, open circuit, the flow is coming inside is quiet anyway, so you don't have to take too much care of it. It will be quiet if it's suction. Once it is blowing, it's another story. Once you have a blowing type, it will be noisier. I was mentioning it at the beginning. You would better look for a way to put your motor outside the working area. It will be much preferable. If it's a open circuit, you put your suction fan right in the window or even outside. Once you are operating, there is no noise. It's only for the neighboring classes if it's close to the building. But for you, for the lab, it will be quiet. And the same with the closed circuit. Okay. I bring here the examples of two wind tunnels I was instructing recently. The one that you see is the open loop in Azrael in Jerusalem. It's looking downstream. To the right, it's the contraction, the nozzle, and then you see the transparent test section, and then the diffuser, and the fan is outside. Practically, this tunnel the cost was 5 times cheaper what I did in Tel Aviv. Also, the test section is a bit smaller. It's 30 centimeters, where in Tel Aviv it was 50. As I mentioned it yesterday again, you can run visualizations with smoke fog as much as you like. You just inject and everything goes out. Just, I said yesterday, make sure people are not sitting outside having a tea time or smoking time there when the fan is blowing the stuff. It's not dangerous, but it's not pleasant. So this is the open circuit. The closed circuit wind tunnel, which I was instructing in Tel Aviv, this is, you see, the top view of the layout. You can see the walls through there. And the leg of the fan is outside. It's in a patio that is unused. It was unused. So it was win-win situation. We put out the fan outside the class, only the test section and half of the other legs. So we could gain space and gain quiet, and it's a nice layout. Only thing is, in such places you are limited by the walls, and it had to be iterated several times according to the diffusers, and the expansion angle of the diffuser will determine the size and the contraction. There are actually two elements there which are determining the size of your tunnel. One is the contraction ratio, namely the area entering the nozzle and the area of the test section. And the second factor is the expansion of the diffuser, the total angle of the diffusers. In closed circuit, you have two diffusers. One is out of the test section, and the second diffuser is from the fan down to the third corner before the corner of the settling chamber. We can go over the elements there if you like. Let me see there, I can see you and then. Let's go over the elements of the wind tunnel there. We start with the test section. And then you have a diffuser from the test section to the first corner. In this case, it was the diffuser was manufactured, designed from two elements, but it doesn't make any difference. It's continuous. And there is the first corner after the test section. Then there is a possibility again to have a diffuser between the first corner to the second corner, but cost-wise and design approach, you would like this to be constant, so you have two identical corners and turning vanes. You don't have to design twice, and you don't have to pay the manufacturer for two different elements. Then there will be a short section, circular or square cross section to circular of the fan. And we'll say it again, we'll mention it again. The fan area, let's say the free area, the flow area, because it is blocked by the central part of the fan, would be twice to 3 times bigger than the test section. That's a rule of thumb, to have the flow there slower than the test section, because then you decrease your losses. If the velocity in the fan was so high as in the test section, your losses would decrease significantly. So as a rule of thumb, you look for a fan with twice the size, cross-section of the test section. So there you have another section which again
This hydraulic radius, how they are going to compensate?
please repeat.
Hydraulic radius, the radius,
Tell me.
the radius, how they are going to finalize
Yes.
the radius.
What is your
Like, corners, radius will be there.
Corner guiding.
we'll talk about it. We'll talk. He's asking about the corner, the vanes. We'll discuss it. We'll elaborate on that. I'm just mentioning the layout now. Then we'll go inside and see what's element by element, how we take care of it.
So this fan area, it means like diameter of that fan and how?
Less the central area of the knob, because flow will not go through this. What you care about is this velocity, the speed in the section of the fan. You don't want the speed there to be too high. As high it is, your loss increases in power of 3. It's according to velocity.
So the diameter need to
Oh.
be bigger than that of this section fan axis.
Sure. That's why the diffusers. That's why this diffusing sections. Tell me.
Before the blow down or during the blow down,
Yes.
is the volume air inside the duct is same, or some you have to pass out some air, or some sink you have to take from atmosphere?
If the question is if the same air remains all along.
All the circuit.
So it depends. Sometimes you ventilate your test section to have atmospheric pressure. Sometimes you keep it closed. But of course, once you ventilate, you will have losses. So you have you have to consider and decide what you prefer. Once the advantage of opening this ventilation is that you are losing more energy. The advantage is that you don't have to care too much of hermetically closing your test section. There will be no leakages. Once it is hermetically closed, it will be lower than atmospheric pressure. And I don't know if it's an advantage or not, because then you can hear if there are leakages. And you have to take care of them. So from there we go to the some section again, transmit, transpose from round cross section to square or rectangular, and then you have the third corner, and again the fourth corner before the prior to the test section, the settling chamber. Again, you prefer them to be identical if possible, not to take care too much of diffusing the size there, so you save again the double design cost and manufacturing efforts. Don't forget, keep those sections movable. I mean, we'll talk about the turning vanes. Even turning vanes, you would like them to be removable, so you can take care of them. Sometimes you want to replace. I didn't mention here the heat exchanging on a closed circuit. Most likely you will need to cool the air, because if you run long time, energy is heating up. Depends on the speed and the environment. It's not a big deal. Actually, in low speed, sometimes the heat exchanging is very simple. They just put some AC system and that's it. I mean, venting, and they don't care about simple system like home system of AC, and once it is far away from or prior to the fan, you don't care too much about noise, acoustic noise or noise in the floor, because then anyway everything will be mixed in the fan. So what happens before ahead of the fan is not so critical. So usually you would prefer to put this heat exchanger ahead of the fan, but there are wind tunnels that you are using your vanes in order to have some pipes and cool your system, which will be, I mean, manufacturing turning vanes to include the tubes will be cost-wise. So maybe it should be considered. Oh, okay. Let's have a coffee break, and we'll continue. Any questions just before we get out? I don't want you to be curious. Dr. Alu.
Where is the fan?
Fan is there. The fan section is here. In this thing is here. It's. I'm sorry. I apologize. I apologize that nomenclature is in Hebrew. I was not working. Yeah, this is the section. Maybe I'll go section by section so we can write down. I forgot to. Oh. So this is the test section. This part is the test section. This is diffuser. First diffuser, second one, but they are, I mean, not second diffuser. It's part one, part two of the first diffuser. This is the first corner. numbers are different by the students. They put some different numbers, but once we started with the test section, everything starts from there. So the first diffuser, first corner, and then constant second leg, and then you get to second corner, and then there is a short diffuser towards the fan. So the diffuser, there is a diffuser here, there is a heat exchanger section which is not used now. In this layout, we just kept it, kept the possibility to have a heat exchanger there, and there is this section that transforms square to round. It could be, all these three sections could be replaced by one diffuser that also transpose rectangular to circular section of the fan. This is a section that again transform the shape from round to rectangular. They are short, but this is mainly because that in that project students preferred to let that work done by the contractor. So all these sections were metallic, though the wind tunnel was made out of wood. These sections around the fan, they are metallic. And then getting out from the fan, you have this second diffuser that was made out of 3 parts. It was made out of 3 parts. And you have the third corner, which is the largest, the same as the fourth corner. They are identical, the corners. I mean, the turning rates are identical, and there is a fixed constant area section. This is the fourth leg. So we have the first leg, second leg, third and fourth. Following the fourth corner, you have settling chamber, constant area, which will include all your attenuating elements, if it's honeycombs, meshes, whatever you put there. And that's it. And then the nozzle, most important, I forgot to tell you. In Tel Aviv case, the ratio was 1 to 8 almost. Or 8 to 1. We'll talk about it. We'll elaborate on the nozzle later on. So we'll have a break. rectangular to round shape and so. Okay, sorry. This is the final shape of the wind tunnel after it was constructed. On the right photo, you see the outer leg, the leg which is outside the building. This is a patio that is unused one. And you see down is the second corner and then the constant section, and then it is actually small angle diffuser, and then there's a constant section, and then the fan. You see the fan section is metallic. You see this, the fan section? This is the section of the fan. It has one section transmit the rectangular to round, and there from round to rectangular, all by the same manufacturer. Usually you would like to have one manufacturer for all these elements, so it won't tell you, it doesn't fit because the other one was making a mistake. You should take and give it to contractor, will take all the responsibility. And if not, you'll face problem, for sure. Even there were three contractors. One is the kitchen furniture, the kitchen carpenter, who was making the all layout of wood. And then there was a constructor for the test section, it's another one. And the third one is the guy with the fan. So fan to the wood structure was not a big deal. The test section, because there were two different manufacturers, always one was blaming the other. It was not right, he was putting the holes not in place. So we learned from that, I learned from that. I mean, I knew it should happen, but you know, students are very busy. They have exams, they don't have to follow up what's going on, what's going outside. They give you the work and they think, you know, shoot and forget. Doesn't work like this. You have to follow up and see what's going on, day by day. If not, you'll get it. So at least these students, I was sending them to the carpenter to watch what's going on. The test section was there. And we told them, look, you connect first, and then we'll take. Once you connect your nozzle to the section and we see it smooth, then it means you did your job. So anyway.
What was the cost of this?
I said overall cost was like 500,000 shekels, which is 75 lakhs. But it was including some equipments. It was including the controller of the fan. It was including the measuring, the force measurement system, which are not cheap. They are not cheap. They are usually the same order of price as the wind tunnel.
The section is made of Aerospace, or?
Yes. Aluminum frames and perspex. It's ready-made. There is a company there which is specialized in such constructions, and it's very easy for them to make this.
Length of test section is? Length of test section.
There also, we went for, the question is what the length of the test section. Here it's 3 times the dimension of the cross section, which means 150 centimeters. Same as in Jerusalem, where it is 30 centimeters square, the length is 90. Next section, we are going through components of raw circuit wind tunnel in general. Some of them we have mentioned already, most of them. Let's see if we missed anything. So, minimum 2 lengths of the test section, 2 lengths of the largest dimension of your test section. If it's rectangular, twice the longest leg. But I prefer the three times. Yes.
The maximum dimension of the cross section or the model?
We're not talking a model today. He's asking about the dimensions of the cross section or the model. Now we are talking just on the wind tunnel from now on. We don't talk about the model. Model is just referring to, but we talk about the test section. At least twice. You want it to be at least twice because you have some measurements you would like to do downstream. For instance, you can measure drag by direct measurements of force. But in two-dimensional airfoils, you can measure drag by integrating the velocity distribution in the wake according to momentum conservation. So you want it to be fairly downstream. Now, if you put your model in the middle of the test section, you have to go further downstream. So it has to be some distance to go. So that's why 2 even is not enough, because once you're in the middle, then you are left with one length only, and sometimes it's too close. So 3 would be enough.
What about the permissible aspect ratio? Any length to weight ratio we can select of the cross section? Or is there any limitation on that?
Limitation on what, please?
The aspect ratio of the cross section, length to weight ratio.
It depends on your mission and your planning, what you are planning to work to. If you know a priori what you want to work with. For instance, if you know always you will do two-dimensional work. So you will, practically you make it rectangular, because then you put your profile, airfoil, across the short leg, and you will have a lot of space to sweep, right? Because, and if it's rectangular, it's a waste, because you then have to have very long span, what you need, because two-dimensional, you can be satisfied with usually aspect ratio of 1.5, 1.6, something like that, between the lengths to the widths, just like that. But that's dimensions you can find. Every corner will contain turning vanes. We don't let the flow just turn freely, because then it will build up a velocity gradient according to centrifugal movement. So we have to break the bulk flow with vanes in the corner. So all corners will have turning vanes. Sometimes you put safety screens in order to collect any foreign bodies, unidentified foreign bodies that you lose from your models. I prefer not to have it. It's not uneducational to let somebody think that you can lose something of your model. I don't remember in my long years of working that we were losing any, undeliberately, any part of a model. It has to be designed well and no accidents in the tunnel. So even now in Jerusalem, my engineer was telling me, why don't we put collecting screen? I said, no, it's uneducational. I want people to know there is no chance of accidents there. Once it happens, it will tear out the meshes and everything. So we have to be careful. So we were going through the sections one by one. Nothing else is here. There is an option for wide. I put here an optional wide angle diffuser, which I don't recommend to have it anywhere. If it's far away from the test section or settling chamber, not so bad, but I think in our case you can find wide angle diffuser only ahead of the fan, where anyway everything is going to garble there to be mixed. So I'm not so worried about it. But as long you go and you get closer to settling chamber and test section, you would prefer everything to be streaming quiet and get ready to be uniformly distributed in the test section. So with that, I concluded this overview of closed circuit, though we shall get into it in details later on. Open circuit will have less elements, obviously. And this is again the layout of the wind tunnel. Recently I was instructing with the students. Starting from the right end, you have a section which we call settling chamber. This is the section that take in fresh air. What should we do? The right end, most right end is the settling chamber, and you see a lot of drawers there. There are a lot of drawers there.
Excellent, sir. Is there any area ratio, some constraint is there for designing the settling chamber?
Settling chamber, it's according to your constraints. There is nothing that you can say it has to be certain amount, certain lengths of its dimension. Usually it is one dimension of your largest dimension of the cross section. Typical the settling chamber size would be one dimension, the largest dimension. So it's a cube, usually. It looks like a cube.
So settling the air,
Yes.
the turbulences, there should be some space.
The settling of air is being done in the settling chamber by the elements that we are inserting there. You see the drawers we put there, starting with a honeycomb, and we'll talk about it in detail later on. And then you have meshes, screens, one by one, and decreasing porosity, starting with open and then closer once downstream. So this is making this settles the noise in the settling chamber.
Settling chamber, there is some velocity limitation.
No, you just
exceed some values.
no. This is the aspect. This is the contraction ratio between the settling chamber and the test section. Usually, there is a let's say rule of thumb to have contraction ratio between 6 to 9. If on the lower side, the advantage of the lower contraction ratio is that boundary layers are not developed. They don't have enough time to develop. Where your ratio is big, then they are starting to develop already in the contraction. So this is some compromise between big boundary layers. The advantage of higher area ratio is that you reducing the noise. If you have turbulence level of certain amount in the settling chamber, once you are reducing your shape, it reduces also the size of disturbances. So this is the advantage and disadvantage of contraction ratio. What do you think? It's okay? Okay.
Is there any other construction than the honeycomb, sir? Is there any other construction than the honeycomb?
No. Usually there are certain shapes for honeycombs. We'll talk in detail on that. We'll elaborate on that later. Just mentioning the elements, and later on we'll elaborate. So we have this settling chamber, contraction, the nozzle, test section, and then the diffuser and the fan. That's all. Very cheap, very few elements, not so much stories. In our tunnel, I added settling chamber on the backside also, just for instructing purposes, to see some effects, and at good show. You wouldn't like noise from the fan to revert and climb back to the test section. It's slow speed, so you may have some noise climbing back from your fan, right? Some acoustic noise.
Settling chamber after the fan.
Yeah, no, before the fan. Between the fan and the test section. You don't want acoustic noise to climb back to the test section.
So between the diffuser and the fan, you have a settling chamber.
Here.
Between
Here. Another section was added to have capability of inserting certain elements, meshes, even honeycomb, because in the fan section it influences the flow there, and it rotates the flow. You don't want anything to climb back. So this is something we should check thoroughly later on, how much it is helping us to quiet the flow. I put there another option of open loop with a blower. This type of wind tunnel was constructed in the Technion recently. A colleague of mine, professor in the mechanical engineering at the Technion, he was constructing a blower type. I believe this type of wind tunnel cannot be too quiet. It should be noisier. It will be noisier because of noise coming from the blower. The big disadvantage is that you have the blower in your office. It's inside the building. Okay? To start with, the blower is inside the laboratory, and you cannot rid of the noise. But in terms of flow quality, you start with incoming turbulent, highly turbulent flow, and you have to take care of it. That's why it doesn't care of this wide diffuser, because anyway, the blower there is very noisy. and then he has to take care of all the noise further downstream. Of course, in the Technion case, all the sections following the blower are much longer because he has to take care of all the noise.
Any advantage of this or the previous one?
Advantage of this, I cannot say. I cannot find. I didn't find too much. I didn't find. Low cost, maybe low cost. Yeah. The centrifugal blowers will be cheaper than axial one because these are simple vanes that are moving the. It's not. There is no sophisticated design for these blowers. That could be the only disadvantage. They are just pumps.
The velocity will be varying with the RPM of the blowers. Velocity of the flow.
What is the question?
The velocity of the flow in the test section
Yes.
is varied by the RPM of the blower.
Yes. Now, of course, you could put your blower outside the laboratory as well. So you will save the noise, but then you will have to take care of the incoming air. It has to be cleaned and filtered, all the stories. You have to take care nobody is sitting there having his break, smoking or what, I don't know what he's doing there.
Here in the test section we can have higher pressure,
Yes.
higher than the atmosphere.
Yes.
Whereas in the
Yes.
case of fan, we
Yeah.
can have only the atmospheric pressure.
In the suction you get lower. The suction your pressure is lower. Now in open circuit, the power needed and the main factor of
Sir,
power.
one point, in
Yes.
LA tunnel, this closed tunnel, it is a blower type or fan type? This tunnel.
Closed circuit, it's no question. I mean, the question is if closed circuit is blowing or suction. It's the same. One side is sucking, the other side is blowing. There's no question of blowing or sucking. I mean, it's in circulate. It sucks from one side and blows to the other side. It's the same. Anyway, it's an axial fan. It's not. It cannot be centrifugal. It won't be centrifugal.
Sir, why the diffuser is placed before the contraction?
Again, please.
Sir, why the diffuser is placed before the nozzle? It is shown that like that.
On the blowing and the blower.
After the blower, there is one diffuser in there.
After the blower, you have a diffuser because you want to settle your flow and to have. Excuse me. Ask me. I'll answer you. Believe me. You have a question? I'll answer you because if you have a question, it's probably interesting everybody. The question was, why is the diffuser? Can you repeat?
Why the diffuser is placed just after the blower, and after that there is one contraction here.
Yes. No. This is schematic, but this is the way it's done. I mean, just could be the diffuser is longer and the settling chamber will be longer, of course. But in principle, after the blower, you'll have diffuser because you want the reduction of noise to be done by meshes and honeycomb, and they have losses. And as faster the velocity is, the losses are higher. Right? Because as it flows, as in pipes or any other flowing element, the head loss is proportional to velocity squared. Right? You remember this?
Plus, is there a difference if you place the diffuser after the section?
The purpose of diffuser is slowing down the flow. The purpose of slowing down the flow velocity is to have less loss. when you are using some elements, any element. It could be the turning vanes. The turning vanes, you want the flow to flow there as slowly as possible, because if it flows fast, you'll be a lot of separation and storage. So that's why the sections for the turning vanes are the largest in the neighborhood. That's it. There is no other purpose for that. You don't just diffuse the flow to have fun. You diffuse it to get to the fun. And then you diffuse it here to get to the settling chamber with low velocity. This is the, schematically, this is the settling chamber. It's very narrow here, but usually it will be wider. And it will include all these elements to reduce turbulence. So you want them to be acting on low speed as possible. Now the most requiring energy here is the jet power. We call jet power. Once you are in an open loop, open circuit, most of the energy you have to feed in is to accelerate still air to the velocity in the test section. So this is the power jet you have to supply. And this is the main customer, consumer of energy in the open circuit. In comparison to the closed circuit, the consumer of power is what? The losses all through the circuit. Once you accelerate the speed to the design one, the energy you need is only to overcome the losses in the circuit, but not as in the open circuit. In the open circuit, you have to maintain and feed in energy to accelerate still air to air in the test section. So this is a simple relation between velocity and power. Simple formula. I don't know why it didn't come out.
Why it is linear? In the equation it is.
Look at the axis. Look at the axis. What type of axes are there? You see the axis? What type of axes are there? Log. First course in measurements and testing. This is something I recommend my students on the second year, first year. They must see how to test and see. I mean, yeah, okay. So it's like that.
Power is kilowatt per meter square. Meter square of what, sir?
Test section.
Test section area?
Yeah.
Cross section area?
Yeah. So in this formula, which is not, it's a new paper, but it didn't come out in the slide. The power in the test section is half density times area times velocity power of 3. This is the power required to maintain flow in the open loop. Once you have all this information, which we didn't work out, but you will have, after you calculate the loss in your circuit.
Sir, if you don't mind.
Yes, please.
The equation, how we got it?
This is,
Kinetic,
it's kinetic energy, simply kinetic energy.
that is half mv square.
M dot V squared. M dot, the question is how we get this formula.
Half mv square. Half m dot v square.
Half M dot V squared. Now M dot is U times area. So you got V triple, V third power. You have too many questions. Ask me, please. Were you asking or he was asking? Discussing. So maybe it's interesting. Everybody here, no? Tell us. What was the discussion? Not
For the equation.
for the equation? Okay. So now is it clear? Okay. Don't be ashamed. I mean, if something is unclear to you, I'm sure some others also will be interested to understand what you don't understand. So let's make it loudly. Once we have in hand the information about the loss and the power required to accelerate the flow, then we can talk about the fan, the power we need in the fan. And in this course, I'm not designing a fan. I didn't take anywhere, even in my wind tunnels, I was not taking care of designing the fan. I think it's expertise that if you want, if you like it, it's fine. But there are a lot of manufacturers that can supply you any fan that is required to you. And we'll do this in hands-on last day. I'll show you. I was requesting that you will have your own computers in the hands-on. I don't know, maybe we'll see it in some computers laboratories and we'll work there. You can get into such this manufacturer of ours he has a web where you can get in and insert your details, information, and it comes out with a lot of selections of fans. And you just have to put yourself where is your working, what's the most working point. And according to that, you choose your fan. The axis here, you just don't see here the point, the working point. But the axis here, the horizontal is the RPM. The vertical is the static, is the pressure. And you have two verticals. To the right, you have the total power. And to the left, you have the efficiency of this fan. So, and the bold line is a characteristic of the fan that you were choosing in this case. It is said here, some model, I can see angle of the blades 35 degrees, 2990 RPM, and so forth. So the bold line falling from 2700 down to 0 is the static pressure the fan facing. So if you are blocking your fan, namely it creates a vacuum there, your flow is 0. You go down to the horizontal axis is the flow rate in cubic meters per hour. So you will have 0 flow in your fan when it is blocked. What to do, right? If you block your fan, there will be no flow. But then, in that space, small space between the entrance to the fan and the blades, you'll have a very high static pressure under negative, right? So you see the pressure is very high. Very high. It's beyond 2700. You get 0 flow. Once you increase or decrease the negative pressure, you get more flow. And probably, let's say our working point will be somewhere here. Let's say because of loss of energy and the jet power will be there. The total pressure out of the jet power and actually jet power is dynamic pressure, and then the pressure loss in the circuit is again pressure. You sum up and you get some pressure that the fan will have to work against. So that's the working place, the working point it will have.
Generally don't take the most efficient point.
Yeah, you do it, and once you know where is your working point, you look for a fan that will have the best of best. So it's again iterative process. You will look for the fan that will work most efficiently, but then maybe it's much more expensive. So it depends what you want. To pay for the electricity, it doesn't go from your account, from your budget. It goes from the building, and then, but the cost for the fan, it's your budget. So something you have to consider.
This borderline is intersecting at zero
I think-
static pressure.
Tell me.
This borderline is intersecting at zero static pressure. What is that indicating?
This indicates that your fan is free, is not connected to anything, just the fan. Both sides, it has atmospheric pressure. That's it. So you have a full. This is the performance of the fan. This is first thing I was checking when we got the fan. I told the guys, hey guy, come and measure the velocity on the surface of the fan and see that they supplied what they meant. Surprisingly, I found, first of all, that the RPM is higher than what they committed for. I don't know why. I mean, I see in the report of the students that the RPM is 2860, and when I measured with a stroboscope, I found it's 2990. So something, I don't know why, but I got something better, but what they paid for, but maybe they were mistaken in the report, I don't know. And then they measured velocity distribution in the surface, and they accumulated it to get the flow rate. And it is exactly what they meant. The only mistake my dear students made is they were calculating the speed in the test section according to that point, not to the working point, and according to the 0 point. So the theoretical velocity they wanted to have, 80 meters per second, couldn't be reached after the tunnel was connected. It dropped down to 50 meters per second, which is fine with me. I don't care.
The selection depends upon the flow rate only. In the test section, we know what is the flow rate.
Please repeat. Please ask loudly so I can understand.
See, in our test section, we know what is the airflow rate.
Yes.
Cube per hour.
You know what you want.
Yeah. So
The question-
that decides the
You know what?
requirement and
You know what? It's iterative. You know what flow rate you want in the test section, okay? But for that flow rate, you have to calculate your loss. You have to add the pressure for the flow rate you meant. You have to add the loss you have, and then you are not zero loss. You are not zero pressure. You're coming up to 1200 pressure, and then your flow rate will fall down immediately. You understand what I'm saying? You need your jet energy is something like that. The pressure you need to suck for your jet power will be here already. It won't be zero. The pressure out, once you connect your fan to your tunnel, the fan will feel lower pressure. It sucks, right? And there is some resistance of the flow to flow. So there is some negative pressure in front of the fan. It has to work against some pressure. One contribution is the jet power. It has to accelerate the flow from 0 to test section speed. That's the main issue. Let's say you may calculate what's the power of 80 meters per second in that cross section. You just take that formula and find out what's the power needed and what's the pressure there. So that's the pressure you'll feel ahead of the fan. And then you have to calculate the losses from the walls, friction on your circuit, on your tunnel, right? there are losses. In the meshes, in the honeycomb, in the contraction, there are losses. You have to add it up, sum it up, and you come with higher pressure that you have to work against. Let's say you be here. Let's say you get here, you get the practical flow rate will be only 15,000 cubic meters per hour. You thought you will be 28,000 per hour. What is the free fan? That's what my dear students were doing, and I was not too close to follow them. So you come out with 50 meters per second, not 80 meters per second. That's what the fan can supply. If you were insisting of having 80 meters per second, you should have picked higher power. Is that clear? Before we break, anything you want me to talk about?
Sir, in one of your wind tunnels,
Yes.
you had a wide angle diffuser just before the fan. You said that because it will be a noisy flow there, you wouldn't be caring about if you had a diffusion and you can recover some area. But then, as you just said, that the fan has to create a suction in front of it. Wouldn't that cause extra resistance because you have the slowing down of the fan and you have some extra pressure building up there in front of the fan? Is it advisable? Is it a good idea to have a wide angle diffuser in front of the fan?
Mm-hmm. Yeah, you want.
Because that will cause an resistive pressure in terms of suction.
Why do you say so? Why do you think so?
Because stream-wise flow, you have the increasing pressure in front of the fan. Just in front.
The main energy you have to contribute for is in the test section. You accelerate the flow from 0 to test section speed. This is the main energy. Later on, losses are only due to friction, nothing to do with pressure. Even if it diverges, I mean, static pressure will increase. And the pressure we are talking here is negative. This is negative. This is pressure you have to work against, to work for sucking. I mean, the jet power is something that you have to build. So it's negative, right? Is that answering what your question, what you asked?
I'm not sure because what happens is like anyway you have an adverse pressure against which the fan is working because the fan is creating its own pressure, right?
Yes.
But in front of the fan,
Yes.
a bit upstream of the fan,
Yes.
if you have
Diffuser.
if you have a diffuser,
Yes.
then the flow will see some extra resistance while getting accelerated.
I'm saying on the contrary, because the pressure you're talking about is negative, and once you have a diffuser, the pressure is increasing. So it's decreasing the negative pressure that you have to suck. You have to work against lower absolute value. That's what I'm saying.
What is that then? PW in
Power.
What about the power?
no, what means flow rate is increasing, but power I think it is almost constant.
Yeah. Yeah, the power is something that the supplier is giving you. You work in the maximum power. This is a maximum capacity.
Usually jet power is more than the losses. No, sir.
Sure. Sure.
But we have to have a fan to take care of jet power.
That's the main issue. I mean, once you build your open circuit, it would be easy life. Don't calculate too much, don't bother too much, just take the jet power, let's say multiply it by 1.3, another 30% for loss, and that will assure you that you will run the velocity you wanted. Because if you buy the exact jet power, then you'll fall down. That's for sure. But to be more professional, you make it iteratively. You choose one of the fans and you start calculate what happens in the velocity that you intend to have, and see what are the losses and what final velocity you get. If you get lower velocity than what you designed, then you have to look for higher power and so forth.
So generally, what is the factor between losses and the jet power?
Roughly, I'm saying it's like 25% the losses to the jet power, or 30%. Are you ready for lunch? Is it lunch break or not yet? Just a break? We have 3 hours now?
Lunch is 11:45. We have another half an hour, 40 minutes.
So how it goes? So we have 3 hours according to the plan? Or what is the problem?
It's actually 2 hours.
So how is it going?
We took the first break little early actually.
You think?
It should have been at 10:30.
I see. Okay. No problem. We have time. Just let me know if you want to break, we'll make another break. But if you feel comfortable, we'll go on. We'll go on. Okay. So, following the questions, recent questions, the closed circuit tunnel requires power mainly to overcome the loss. It doesn't. You don't calculate. You don't need power to accelerate, continuously accelerating your flow. But once you accelerate it, it will maintain. But again, just for the easy way of choosing your fan, you can calculate your jet power, even in the closed circuit, and take it as a reference, because everything will refer to that. So let's say this: if you buy a fan for the closed circuit that can supply a full jet power, then you are set. You get the velocity you wanted. No surprises. And also you get some extra power, and you shouldn't run on the maximum of the time. You can run lower power, lower noise, and whatever. Let's see. Oh, I'm sorry. Something happens here. Wait, maybe. I don't know what happens to this. Let's break 5 minutes. I'll check what happens with the slides. Why is it not showing? Okay, you can call them. I'm working with the PDF. I'll work with the PDF. Anybody was going out? Everybody's here? No? Okay. You want me to wait? Okay. Let's talk about the energy losses in wind tunnel components. We define the dimensional loss in a component by the head loss in that component divided by the dynamic pressure, local dynamic pressure. The dimensional loss, coefficient of dimensional loss, is the head loss in that section divided by the dynamic pressure, local dynamic pressure, then namely delta HL local over dynamic pressure, local dynamic pressure. Now we can define the coefficient of loss of the local section referred to the test section. Namely, we divide the head loss by the dynamic pressure of the test section. Doesn't move, huh? What happens to this? Okay. So in order to get that, actually, I don't know, in your paper, in formula 417.1, denominator should be half density, local density. Okay? Obvious. So you see that the local energy loss is, or the total energy loss, first of all, the local energy loss is the volume rate times the coefficient times the dynamic pressure, which is coefficient times the kinetic energy. Now, if you want to express the local non-dimensional loss or coefficient, we have to multiply by the dynamic pressure, the local dynamic, and divide by the test section dynamic pressure, which is the power jet expressed by pressure, and the coefficient relative to the test section, it equals the local times the local dynamic pressure divided by the test section. And finally, the total energy loss is the summation of all the head losses in the sections, in all sections. So PC, the total power loss, is the summation of all the totals, all the losses in all sections, time the power in the test section. And the next expression that we use is the energy ratio. Energy ratio is the jet power divided by the total loss of the circuit. See, that's what you were asking. What is the percentage between the loss and the jet power? So the loss is like, in the cases I was working now recently, it was like 25%. So the ratio is just inverted, 4 times. So the energy ratio could be like 4. Just see that the nominator is P sub T, not P sub L. In this formula, the 419.1, the total, the jet power is PT, power T. Sometimes it's confusing the pressure and power. P here stands for power. And we are dividing the total power, the jet power, by the total loss. And in another way, we can write it as the next formula. It's 1 over the sum of all coefficients, which is a smaller number than 1, obviously. So you get energy ratio bigger than 1. So that concludes overall definitions, and now we'll get deeper into calculations of losses in elements of the wind tunnel. Yes.
So the loss that is mentioned is the static pressure drop or the total pressure drop?
Total. It's relative to total. Actually, it's in terms of test section dynamic pressure. Power jet. We all related to the test section. So in the nominator is the test section power.
No, but in 417.1, the first formula, that is total pressure across that section.
That was a local. That was the local coefficient. It's the head loss in a section divided by the dynamic pressure in the local dynamic pressure in the local station section. Is that what you asked?
Yes, so that is total pressure, as in static plus dynamic, that component.
This is dynamic pressure. In formula 417.1, the denominator is the dynamic pressure in the local section.
Okay, and the numerator is P static plus half rho squared. That
No. The numerator is it's the nominator is the loss across that section of dynamic pressure. I mean, whatever it is expressed as dynamic, but it's loss of the total pressure. Okay. So now we are moving on to see how we calculate in each section its loss. And we start with the constant area sections. One of them is the test section, and some others. Anyway, we know from pipes that the pressure loss is expressed as friction coefficient F times length of the pipe divided by hydraulic diameter times dynamic pressure. That's why 421, if you divide pressure by density, if you divide the pressure loss divided by density, you get friction factor times L over D, H, U squared, U average squared, U mean squared divided by 2. And if your pipe or conduct is not circular, you use this hydraulic diameter. Hydraulic diameter simply expressed as the formula for circular. So this way you will not forget what is the meaning of diameter of hydraulic diameter. Just write area of a circle and then instead of simple diameter, write the hydraulic diameter and then get the diameter, the hydraulic diameter out of that formula. If you multiply, you get it. You get this relation. So we are using a pipe flow formulas, but instead of regular diameter, we are using hydraulic diameter. If we compare the pressure loss we showed earlier with the pipe head loss, we get that the coefficient of loss in the wind tunnel is actually friction times length over the hydraulic diameter of that section. And if you go further and you claim and you know that actually the friction is the cause for pressure drop in your pipe, so you equalize the force exerted by the friction, by the shear stress, equalize it to the power, to the the force exerted by the pressures, the difference in pressure in two sections. So this is actually the the momentum conservation law in a simple and final form. So the length of the contact area times the shear stress times the circumference is actually the envelope of that contact times the shear stress. This is one force. On the other side, the pressure is working on the cross-section area, which is ACA times delta. And for circular pipe, you can express the shear stress as that formula, the 4 times T. It's 1/4 F times dynamic pressure. Friction factor is given in Moody's plots for pipes. And instead of going and find the points from the graph, you can use this formula, which is iterative. This one is direct. F is directly expressed. F is expressed directly from Reynolds number and the smoothness, relative smoothness of the surface. So you get friction factor by this formula instead of using the graph, which is a bit sometimes difficult. And yeah, this is small e. Small e is the surface roughness divided by the diameter. And here diameter is hydraulic diameter. What is your question? You want to ask him, not me?
Just D, I am asking sir, what is the
diameter.
Diameter, but it's hydraulic diameter. Tell me?
Is it the same DH or any other diameter?
When you don't know, it's hydraulic diameter. If it's circular, no problem. If it's rectangular, then you are safe. It's the same. Okay, just definition of coefficient of friction is the friction factors times U average divided by U max squared. If it's a circular cross-section, you know that the velocity in the center is twice the max. I mean, the velocity, the maximum velocity in the center is twice the average velocity. I think we're done with that. Are we going to the next thing? What is the time? What is the no? When is the break? It's 45 or 30? Yeah. Okay. Okay, we'll start the next one. Just a second. We'll move on. We'll move on to the components one by one and calculate the loss and the rough elements of designing them. Let's see. No, there's a problem. Some problem here. I don't know why. Yeah, it looks like I didn't put any textbooks there, but let's see. No, because I will always convert it to PDF the same moment, and that's why I'm using the PDF. No problem there. Anyway, if I need something to go to for any movie or something, I'll find out. Let's see. Okay, let's work with the PDF. We're starting from the test section. So we accept the fact that we want to work in a rectangular test section. Closed one. Big wind tunnels, we don't care too much, because if it's full scale, and when you see those photos of full scale aircraft, you don't care if it's oval shape, you don't care if the aircraft is relatively smaller than the test section, you don't care too much what's the shape of the walls. So in big wind tunnels, we don't care too much that the shape will be oval. Actually, oval is more natural because the shape of aircraft is usually, it's non-symmetrical. But when it comes closer, then the calculations for corrections is worse. So we prefer to have it rectangular or square and go on with it. I think this is a summary of what we said earlier regarding the size, the length of the test section, which is 2 to 3 dimensions and so forth. Now in the test section, I'm going to use now some empirical formulas that are given in here and there in the literature, and they are proven to be reasonable. And we have no time to follow every formula, where it came from, what's going on. But we'll see. We'll do the best. We'll try the best. Now for Reynolds number million, and for L over D 3, namely length of the test section 3 times the long dimension, typical dynamic pressure loss will be in the order of 3.5% of the jet power. 3.5%, which is not so bad. Yet, for open jet, it will be 20%. See what is the loss. Relative loss. What's his name? I forgot your name. Shibab? Shubham. Roughly, the comparison between the loss of closed test section to open test section, you see 3.5 versus 20% for the open test section. And you have this correlation formula to calculate your loss factor there. I don't see where I'm using this relative Reynolds number between the local and the test section, putting in the area ratios and Mach number. We are not using it. So you have, this is an idea of what you're going to get in open and close, but practically to calculate the head loss in the test section, we just look at Moody's, put in the pipe formula, and we get the coefficient of loss. We'll do that tomorrow. No, the last day. In the diffuser is the worst destroyer in terms of loss. And these are the definitions of the diffuser. You have this the angle, expansion angle. We deal with the half semi. There is the entrance diameter and the exit diameter, and the aspect ratio, which is the ratio between the exit to the entering area. Just for you. Yesterday I mentioned the films of editor was Shapiro. I have a film here. I got it from the web, showing how diffuser of 7 degrees is separating flow. Let me show you this in a second. I hope I'll find a I don't know. Allow, see if it works. Oh, it works, surprisingly. Hopefully. No, yeah. Now we are going, I'm not going to show you all this because this is, then I'll have to go over all my course in fluid dynamics. I don't want to do that now. Just reminding you some points. Stefan Klein is a known guy in fluid mechanics and turbulence research. I'll give him some respect. Well, what's going on?
These patterns are often quite surprising. What appears to be a small shift in system geometry can change the entire flow pattern.
I'm not going to do all this view graph.
But it
is later on explaining how we're performing this flow. It's a channel, water tunnel, with a hydrogen bubble generator. Simply wire that you are feeding it with high voltage, pulsing, and you get all these traces. I'll move on just to the point I wanted to show you. I hope I remember where it is. If not, we'll...
You see a thicker boundary layer now. This low velocity region has to decrease. At that time, diffuser to a total angle of about 7 degrees.
Now it's constant.
Is called a laminar boundary layer.
Wait.
Notice how the velocity drops sharply near the wall. And in this region, the particles slide evenly over each other. This low velocity region is called a laminar boundary layer. Now let's open up the diffuser to a total angle of about 7 degrees. The increasing area of the passage causes the velocity to decrease and the pressure to rise in the direction of flow. Watch a streak square in the middle of the passage. You can see the deceleration.
I think that's all. I mean, you see here, these are, what line are these? We were calling them yesterday. Timelines, exactly. That's the meaning of timelines. You see here the wire that generating those timelines, and they are developed according to the flow, regime. So you see here the boundary, the boundary layer here, and here you see it starts to separate. 7 degree, no good. Okay. I recommend you. They are nice. Though they are old. I mean, it's from the 1960s. I mean, nothing has changed in fluid mechanics since then. So you can look at them. It's nice. And these are really big shots in the field.
What it also depend about the downstream distance till which we are using. One is angle, but another is if the diffuser is shorter.
Yeah, you can stretch your luck. Yeah, it doesn't. It may not separate immediately. It depends on the length. Yeah, but you see here, if you non-dimensional this, you mean it's one diameter. It's already separating. Now we define this expansion angle, or we get it directly from geometry by those formulas, either by the hydraulic radius, which is, either the hydraulic radius, which is half of the hydraulic diameter, or you express it as a function of the aspect ratio. This is there. It's the same formula. So the energy loss in the diffuser is composed of two elements. One is because of friction, and the other one is caused by the expansion. Now, for the friction part, you get this empirical formula that Kf is depending on the aspect ratio and the friction factor and the expansion angle. So this is the trade-off. Once this loss is a function of your expansion angle. As smaller it is, the loss is higher. That's the compensation. That's the trade-off. Once you decreasing your angle, then you get it in a loss, because the denominator is smaller, so it multiplies in a bigger number. And the expansion loss is composed of those elements, K times this, and Ke is given in the literature in these three options. Once for circular section and once for the rectangular. That Ke coefficient is given in circular and in square one in those regions. Once the the angle of expansion is less than 1.5. These are these figures. Something is wrong there. What it is? I think there is a misprint there. Let me see. On the first row. Yeah, this is for square section. Yeah. Another one is for circular. I have to look back on the first row. Something is wrong there because I don't see the dependence on theta. On the second region, which is more practical to us, the formula is much more complicated, but here it is. And the third region is when theta, the expansion is bigger than 5 degrees. We have another figure. I call you attention to the first region, the first area where theta is smaller than 1.5. We have to check what's the right formula there. I suspect the last zero should be theta, but I don't want to. Okay, it should be there. Theta should be there, but I don't. We have to check. I'll check.
Theta is in degrees, sir, or radians?
Degrees. Let me check on that. I was answering you fast. Let me check on that. I suspect. I'll check on that. So this is straightforward. Straightforward calculation. You have this empirical formulas. We just have to make sure that we are running the right ones, and we'll get the right values. They were running for many designs, and they were proved to be very accurate. The next loss we'll check in the corner. Now it depends what you are planning. We are now here. We are dealing with simple sheet metal that is bent as a quarter of a circle. We are not dealing with profiles here. I had a discussion about that with one company in Canada that this is their job, daily job, to design wind tunnels. So he was telling me that they are not bothering about these profiles. They are going for the simple sheet metal because the difference of loss between sheet metal and profile is not so significant. And the investment in profiles is bigger. So at least in my last 2 wind tunnels, I was working on simple sheet metals, bended. And also, if you run the CFD, you see that the flow is quite nice. Because if it was just bended metal there in free flow, then there will surely be separation there. But once they are in a cascade, so they are this flow setup gives good flow. The only thing is there are some variations between the exact design of the corners. In one place you find somebody, giving an angle of attack to those turning vanes by cutting the metal a bit shorter. So if you shorter the corner, one of the edges, you get like angle of attack. So in our design, in one of wind tunnels we made it 4 degrees in Tel Aviv, and elongated the trailing edge. Simple formula for this, just getting back to the comparison between profiled veins or to sheet veins. The numbers are maybe seem to be big factor, a factor of 1.222, but the total loss is not so significant in the corner, so it doesn't make sense to invest too much on profiles there. And the overall loss of the corner can be computed as that formula, depending on the Reynolds number depend on the code. That's it.
So angle of attack you decided based on CFD.
Yeah, you can work it out with CFD. Yeah. But usually what you do, you see so many design recently, and some people were really investing in checking all kinds of setups. The one we picked in Tel Aviv, this 4 degrees, the fellow was measuring the velocity distribution in such a setup, and he got a really good uniform. So we just took that one. I think it's somebody from Sweden, I'm not sure. So this was the turning vanes. We go further for the contraction. Now contraction, there are some very known papers. One repeated name is Mehta from Stanford, but I suspect what his origin is. And they came to the conclusion that the best formula for the contour for the nozzle would be a polynomial fifth power. There is a table in one of the papers showing that the fifth power polynomial is giving the best features in terms of separation and turbulence and uniformity of the distribution, of the velocity distribution. So you have boundary conditions on such a polynomial. And what are the boundary conditions for this polynomial? Tell me.
Section size and
Huh?
vein,
Tell me.
the test section diameter and the corner vein exit.
Exit and entering and exit and
Setting channel.
inlet and outlet sections are they are part of the coefficients we have to know, but we put it already. Yeah, if you take a fifth order polynomial and write it generally, a0 plus a1 power 1 and so forth, a5 power x by 5 power 5, then okay, you need 6 boundary conditions. 2 of them will be inlet and outlet cross section, and you get it here, all the formula already. I gave it for you. I gave the whole formula for you. The other 4 boundary conditions, what are they? First and second derivatives on both in and out. You want the section to be parallel, both entering and the exit, and out of that you get this this nice formula. Just correct, please, that x in the formula is actually it's x. It's physically x divided by length, where is it? I didn't. Here I corrected it. Yesterday I found it, so I corrected it. X is actually x prime over L, where x prime is the physical dimension, and x is it's non-dimensional. So x is between 0 to 1. So if you substitute x 0, what you get? If you what you get in that figure, it's H0. It's outlet. It's the outlet. It's outlet. If x is 0, you remain with H0, which is the outlet, the inlet to the test section, but it's outlet from this definition. And vice versa, if you insert 1, you get HI inlet. So it works. And if you want, you can differentiate and get first and second, and you see it falls. It diminishes. I think we are about late, so we'll have our lunch and then we'll come very anxious to see what's going on. Okay, any questions so far?
So then, if you were video we are seeing, we're talking about laminar boundary line, but
We
is he talking about
we
like laminar boundary line?
no, who says? No, we didn't say laminar. We didn't say laminar. This is empirical features, and we didn't talk about laminar there. The only thing is yeah, on the contrary, we have the friction factor. A friction factor, you have to take in account your surface quality. So it comes only when you are turbulent. You don't expect the laminar flow. It's really fairly downstream. You see our Reynolds numbers starting with laminar, but very fast they'll move on to turbulent. So in the diffuser it will be turbulent. There is no. It's better to be on the safe side. I mean, to assume that you are turbulent there, in terms of calculations.
Talk a bit about breathers, like
Like.
they want to have an atmospheric test.
Actually, I was not planning to have any discussion on breathers. I don't think I can contribute too much on that. Though what is done in closed circuit sometimes, that you are opening the test section. After the test section, you open a gap to let air come in and actually equalize the pressure in the test section and have it atmospheric. You can find it elsewhere. So sometimes you put some symmetrical vein just in that opening, so it'll have a smooth flow, but nothing more than that. And I'm repeating my suggestion to you to build a small tunnel. You will? Yeah, and then it is a really acceptable way when you build something new, especially when you have to invest a lot, to build a pilot tunnel and learn on it and see everything, all the changes you want. If you want to make any change, instead of going to the big design, you make the change in the small one, see how it is affecting, and then you go for the big design. So that will be very helpful. All right, so we'll have a break. Okay, feel free, go.